written 1A, part 1. The equation for the decay of iodine 131 is, and the equation is given. It says name the type of radiation emitted by the iodine 131 radioisotope. So emitted means give off, and what we can see is we can see an electron given off, and what we need to know is that beta decay is. Part 2 to this question asks us to name element Y from the equation of the decay of iodine 131. So what we have to do is we have to balance the equation. So on the left hand side, we can see that the top number is equal to 131, which means on the product side, the total has to be 131. 0 plus what gives 131 is 131. The bottom line on the reactant side gives us a total of 53, which means on the product side, we also have to have a total of 53. Minus 1 plus what gives us 53, that would be 54. And when we look up that element in the periodic table, the chemical symbol for this is Xe for xenon. Written 1B part 1 asks us to calculate the length of time taken for the radioactivity of xenon 133 to fall to an eighth of its original value. We're asked to show our working clearly. So this one we're working in fractions, so the initial fraction that we always start with is one whole number, which is 1. And what we want to do is we want to keep halving this until we get to the value given in the question, which is an eighth. Now, for every arrow given, that will tell us how many half-lives there are. There are 3 arrows, which tells us we have 3 half-lives. From the table given, we can see that xenon 133, the length of one half-life is 5 days. So we do 5 days times 3, which will give us a total time of 15 days. Part 2 asks us to suggest which of the radioisotopes from the table would be responsible for long-term radiation if it was released into the environment. So we can see that we've got 3 radioisotopes, so we want to see the one which has the longest time, and that would be cesium-137 with 30 years. Written 2A, calcium reacts with water as shown in the equation. In an experiment, the progress of the reaction was monitored by measuring the volume of hydrogen gas produced. Part A asks us to complete the graph to show the volume of gas produced against time. The first 2 points have been plotted for you. So the factor you're in control of always goes on the x-axis, you're in control of time. And this should be a nice easy scale for us to do. We can see that it goes up in ones, but we have to start at 0. So we'll do 0, 1, 2, 3, 4 and 5. On the y-axis, this can be a little bit tricky. This is where we have to use our rule, 1, then 2, then 5, then 10. The maximum volume of gas being produced that we have to be able to achieve on the y-axis is 48 centimetres cubed. So the easiest way for us to go up here is to go up in tens. Remember, you have to use 3/4 of the graph paper. The next point is for us to plot the values given in the table correctly onto the graph. And you can see that I've plotted them here. But we also have to decide whether this is a line of best fit or a curve. And we can see that the plots give us a nice curve. So we want to join all of these from the 0, 0 on the first plot all the way up, and not beyond the value given for 5 minutes, and that would give us our second mark. So in this question, it asks us to calculate the average rate of reaction in centimetres cubed per minute between 1 and 4 minutes. We have to show our working clearly. So the first thing we want to do is write out the formula. Average rate is equal to change in quantity over change in time. We then want to substitute the correct value. So the time that's been given is 1 and 4. We always do big numbers, take away small numbers. So on the bottom line, we would have 4 minus 1. We use the table to identify the time of 4, and we can see that the volume of gas given in the table is 48. We then look at the time given of 1, and the volume of gas is 32. So the top line for the substitution would be 48 minus 32. This substitution gets you 1 mark. We then do our takeaway, which will give us 16 over 3, and when we put that into the calculator, that gives us 5.33. Part C asks us to suggest a different measurement that could be used to follow the progress of this chemical reaction. So we can see in the question that we're measuring the volume of gas being produced. So that's our product side. So what we can do is we could measure the mass using an electronic balance, and the mass would decrease as the gas was given off. There are a couple of other answers that are given from the SQA. We could also have had pH, concentration, or conductivity, but the easiest one to go with is mass. Part D to this question, a student repeated the experiment at a higher temperature using the same mass of calcium and the same volume of water. Predict the final volume of gas in centimetres cubed produced in this experiment. Now, because we've got the same quantity of reactants, that's the mass of calcium and the volume of water, it means that the total volume will remain the same. If we use the table, we can see that the time taken originally was 5 minutes, and you were given a volume of 48. Even at 4 minutes, we had a volume of 48. So the total volume of gas which would be produced would be 48 centimetres cubed. The temperature would just mean that the reaction would happen faster. So this volume might have been obtained around, say for instance, 2 minutes.